All right, welcome to the morning video. I didn't do a sound check, which is bad, and I lost everything, which is ultra bad. So I've already done probably like 40 minutes, so this is going to be a very short video, about 15 minutes or so. You can see the progress I made. I'm on this page, and I have to go back because I want it all to be on video. So it's not that much. So I'm gonna go back and I'm gonna start the beginning. I have to remember kind of what I talked about, so I'm gonna go back over one thing quick. Now that it's on camera, I have to kind of remember that not everything I said was on camera. In fact, nothing I said was on camera because I didn't do a sound check. Always, anyone listening to this, do a sound check, please. Right now, do a sound check, even if you're not recording. So yeah, sound checks are the most important thing to do when you're recording a video. So let's go down to my activity, and then we're gonna click on this post here. So as a result of this the video that I lost because I didn't do a sound check and I didn't get any audio on it, I made a post here, and let's read the post. So the post is reading machine learning for network and cloud engineers, and then I have a link to so people can buy the book. I'm serving as a advertiser for the author, which I'm happy to do. It's a great book. And then the next line says, blown away to learn that ML/AI is essentially applied evolution/natural selection in code. Absolutely fascinating. And then I have a link here to Khan Academy. And I gave a passionate tangent in the video I lost where I didn't do a sound check. And the passion was we're there's people who deny natural selection and evolution, and I just beg anyone watching this channel to get over that if that's you, and to learn about this. It's fascinating. Why deprive yourself of one of the most fascinating scientific discoveries in our recent times? And in fact, a place you can go is khanacademy.org, and you can learn all about the evidence. So there's a course on biology that covers evolution and natural selection. So I recommend skipping down to this evidence for evolution, because that's why evolution came about. That's why evolution is so accepted in the scientific world, because there's so much evidence for it, and you can learn all about the evidence in this course. So I beg anyone watching this who's skeptical of evolution, who doubts evolution, please, please, please don't be one of those people. Do not deny these hard-won, hard-fought advances in humanity. You're using a computer, you're driving a car, you wouldn't deny those sorts of things. So please do not. So, and I'm sure everyone watching this is willing to accept scientific truths, and even if you don't struggle to do that, check out this course. It's wonderful. Khan Academy. It's all free. You just create an account. It tracks your process. You can even get free AI tutoring from it too. It's just a wonderful site, and I might be doing this module on this channel soon. Okay, so now I need to reread what I've read, so let's try to get through this pretty fast. All right, so how machine learning learns from nature. I find it particularly fascinating, and I'll do another sound check. Okay, it looks good. How machine learning techniques are simply a reflection of phenomena that happens in nature at a different scale. The training process itself is about learning from mistakes, and how we have been able to build algorithms that translate those mistakes into mathematical expression, gradient descent. It will update the parameters of a model towards a small improvement in the right direction. Another interesting analogy is about data diversity and bias, and how models simply copy and learn from what is on the data. including the lack of diversity or hidden bias, much like in real life. We have discussed model complexity and how specific regularization techniques help shape such model complexity to prevent overfitting. In neural networks, a good example was the dropout technique, which statistically disables a certain number of perceptrons in the training process. Such reduction has two consequences. First, it reduces the complexity of the model for practical purposes, lower number of perceptrons active. And second, makes the training more resilient and less dependent on any particular perceptron or input signal, because during the training process it can be disabled at any point in time. This sort of captures the natural effect of making the training harder so that the model can perform better at inference time. I like to make the analogy of a tennis player that trains with one hand tied behind his back. And I'll do another sound check. There we go. The perceptron itself and the neural network architecture are other examples of how the machine learning field copies nature in building mechanisms that leverage similar principles. In this case, a perceptron being a simplified version of how a biological neuron operates. Generative adversarial networks, GANs, as we have seen in earlier chapters, are another interesting example of how two independent entities can force each other to be better and evolve by peer pressure. Very similar to the evolution of adversarial species in nature, where the eagle forces the rabbit to run faster to survive, but as a consequence, the rabbit forces the eagle to fly faster and to have better sight to survive. The process continues, making both better by being adversaries. And something I said in the Lost it's sound check one more time here. Okay, sound check looks good. One thing I said was it's the word better. It's not true. Like sometimes it can make it better, but really what it does is it's about reproduction. So in fact, evolution can make something worse if being worse leads to more reproduction. For example, let's say that the slower rabbit is lazy and stays and just likes to fool around and mess around with the other rabbits. Well, that rabbit is going to propagate more than the really fast one that's kind of out in the world. It gets eaten last. The slower one ventures out of the rabbit nest and instantly gets eaten, but has already reproduced and propagated. So over time, the rabbits are going to get slower, fatter. They're going to get worse, but they prioritize that propagation over exercise or things that may make them better. So evolution, I'm sure people are familiar with the the movie Idiocracy, but that's I mean it kind of drives home that point. It's really not about making something better, it's about making something more likely to propagate. Reinforcement learning is another excellent example of how mechanisms that happen in nature can also be applied to make an agent that apparently knows nothing and can learn based on its interactions with the environment and the outcomes of it in the form of cumulative rewards. We have also seen the power of the crowd in machine learning algorithms. We discussed ensembles where you could have a swarm of smaller models instead of a large model. While each of them is less powerful, the aggregated result of their decisions is likely better than if we trained only one big model instead. A good example is decision trees versus random forest. Genetic algorithms. However, one really fascinating field is the genetic algorithm. As the name implies, it is about mimicking nature's ability to produce the best individual through the survival of the fittest and peer pressure. Nature will randomly produce variations of individuals and test those variations in the environment. The environment enforces survival peer pressure, and only those whose variations make them fitter, which is a different term than better, remember, will survive and produce a new generation. And the process will continue ad infinitum. And the other thing to notice is it can happen at different scales. It can take millions of years, or it can take microseconds. As we see in these machine learnings, they can be trained very quickly. But human evolution, that took a while. Our most recent common ancestor that we branched off from was thousands and thousands of years ago. So your grandmother's grandmother, 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 grandmother was an unrecognizable ape. Yeah. But, like a Neanderthal, like something that's radically different than you or I. We can apply the same techniques, for example, to build ML models that produce the best results. An ML model ultimately results from several choices: algorithm plus hyperparameters. Which one is the best combination for a particular use case is not known in advance. And another interesting way, and I talked about this in my last in my lost audio sound check. There we go. Okay, looks good. You can think of Down syndrome. The Down syndrome happens quite a bit. There's a lot of children born with Down syndrome. So imagine that these children reproduce more than those with not. Over time, all of humanity is going to have Down syndrome, and they're going to be quite a bit different than those that don't, and those advantages will propagate forward. And now it's to the point where they're a different species, and they branched off from a common from an ancestor. Before they came from Homo sapiens, but now they're they're different. That happens over time, and it happens over different time scales. It can happen over millions of years, thousands of years, or thousands of milliseconds. The genetic, and in bacteria, viruses, and this is something I mentioned in my lost audio too. Another great example of evolution you can think of is the pandemic. We all got a science lesson in evolution during the pandemic, in that even though you're vaccinated, even though you've been had prior infection, there's these variants out there. So these simple measures you can do matter, because the virus evolves and it can infect you in different ways. The genetic algorithm models the key steps in the natural evolution process. All right, so these are the key steps in the natural evolution process. The first key step is population. There is a specific set of individuals, each with their own characteristics representing the population that will evolve. In our case, the population is all the possible variations of parameters and algorithms, for example. The next key step is fitness function. However, we need to quantify to which extent one individual is fitter than others. The fitness function is intended to provide an objective quantification of it. We could think in our case would be an accuracy metric, for example. So we're going to think about network and cloud engineering, and we're going to apply these concepts to that. So the next key step is selection. As nature does, it is the process of selecting the set of individuals or characteristics that result in higher fitness. And it's kind of fun because you can apply evolution to everything. If you think about networking devices, they're getting faster and faster. Well, that's an evolutionary process too. You're not going to keep using, token ring Ethernet that's only capable of a few megabytes. That's an evolutionary process. Survival of the fittest. You use the latest, most advanced, fastest networking device with the highest throughput capacity you can find for the lowest price. The next key step is reproduction. As in nature, individuals reproduce, and that results in new offspring that represent some combination of their attributes, crossover, but also nature introduces some randomness in the process, mutations. That will always ensure some level of diversity and ability to tackle new limits. And the last key step is convergence. Some criteria need to be defined as to when the process should stop, whether it is because there is no further material improvement or after a certain number of generations or a specific time. Alright, so this process results in an individual or set of individuals that offer the best performance given the fitness criteria defined. Sound check, just because I'm that flustered from losing 45 minutes. An excellent example of the power of genetic algorithms is Google's AutoML 0. Starting from an empty function, AutoML 0, using the genetic algorithm approach, can automatically learn how to code an ML algorithm. When we look at it in perspective, nature is a powerful source of inspiration for many of the machine learning techniques that we have reviewed so far throughout the book. Key takeaway: try one option, test, iterate. Try another option, test, iterate, etc. Machine learning is an art of try and error. He means trial and error, but much like natural evolution is. So yeah, that's a key takeaway. Machine learning is simply applied mathematics, applied science, but it's from the field of biology, and the specific subject is evolution. It's absolutely a fascinating subject. I urge everyone watching this, take some moments out of your day. It probably won't even take you that long. There's some estimates, but yeah, if you don't have an account on Khan Academy, create one. Use the AI tutor. Khan Academy is a little bit designed for kids, which kind of isn't, but you can get Brilliant as well. But you have to pay for Brilliant. But if you want something kind of more for adults, Brilliant is probably more for adults. But yeah, it's cool. It's like, why does a whale have why does a fin of a whale have the same sort of bone structure as the wing of a bird, as the foot of a dog, as the hand of a human? Because they shared a common ancestor millions of years ago, and then this structure was in the common ancestor, and then due to evolutionary forces, for some of the species, it was more likely for them to propagate if this bone kept becoming larger. For some of them, it was more likely to propagate if this bone kept becoming wider, such as if you needed to swim and you needed a large, wide fin. And then for some evolutionary processes, to have this finger structure made them more likely to reproduce. For other species that went through an evolutionary process that branched off from an ancestor common to all of these species, it made them more likely to have a different sort of finger structure of the bones that allows them to have a tip of the wing that they can use to adjust the lift and steer themselves when they fly. So for species that can't fly, there's a different kind of structure that allowed them to propagate. And for species that need to swim, there's yet a different one. And it's kind of cool because you can see just how similar some of these structures are. They all came from the same common ancestor millions and millions of years ago. Or the science, they could even predict pretty close to how long ago it was. So you can see these animals are all white, because if they were not, they wouldn't fit into the environment. So you can see very clearly these rocks in this picture. So if you're a predator, and this looked just as clear as these rocks, you would very easily be able to identify and prey upon that animal there that we can see is pretty well camouflaged as it is. So the ones that aren't camouflaged all got killed before they were able to reproduce, and the ones that are camouflaged had more time to reproduce. So that's evolution. Evolution is always ever prevalent. All right, so the next section is machine learning framework and tools. And I'm at 8:30. 8:30 is when I kind of wanted to stop. I did lose that 45 minutes, so this is a shorter video than I would have liked. I'm tempted to try to get through here, but you know what? Let's see if I can do that in 15 minutes. It's just reading, so reading typically goes pretty fast. Um, I do have 15 minutes, so yeah, let's try it. Let's take 15 minutes and try to get there. Okay, so the next part is machine learning frameworks and tools. We have reviewed in the previous section of the book Soundcheck. Soundcheck is still good. I don't have to check it anymore. It's because my Phantom Power button was turned off because um, I rebooted my audio interface, and the Phantom Power is off by default, so I just had to turn it back on. We have reviewed in the previous section of the book a wide variety of techniques and algorithms in the machine learning space. In this section, I want to give you visibility of some of the tools and frameworks available for you to practice what you have learned. We will use most of these frameworks in the book's next section, where we describe 10 different practical use cases. In terms of tools and programming languages, there are always personal preferences, schools of thoughts, and beyond. You may disagree with some of the points of view around the tools presented. Whatever tools work for you are the best for your context, so feel free to use what you find more convenient. I will present those I have found more beneficial in my journey and mission. All right, so the first one, and a big one, and it's first for a reason, is Python, which is programming language. First, we are discussing software which needs to be programmed in some language. You can use different options in machine learning and data science. Python, R, SAS, and SQL. From a programming language point of view, I think nothing is closer to Python due to the enormous community around it and readily available libraries. I perceive that one being the major benefit, particularly into context of the goals of this book. So the available libraries in the community are a major benefit. Even beyond that, Python has become the de facto network automation programming language. Some automation platforms give you low-code options, such as Ansible, with the YAML-based playbooks, which I hate. I love Python. It's so much easier to see a Python dictionary than a YAML playbook. It's like I need some formatting in there because I need to know if it belongs to the, it's just white space is harder to read for me than a comma. Ultimately, even if you are not a savvy Python developer, you can find code snippets to accomplish almost any goal. Brute force is your friend, but Stack Overflow is your brother. Automation platforms such as Nornir by Kirk Byers are essentially presented as Python libraries, so you can use them along with your tools in your Python-based automation scripts. Not that learning other programming languages may not be helpful. Go, I think, is a good example of a alternative. However, definitely in your journey to start with machine learning in network and cloud use cases, Python is, in my opinion, the most convenient choice. If you are not familiar or somewhat fluid in Python, I recommend you learn the basics because it will enable you to code by yourself many use cases and prototype concepts and ideas. And if you want to learn Python, there's all kinds of resources everywhere. You don't have to pay to learn Python. It's all free out there. There's all kinds of courses available to learn Python. Python the hard way is probably my favorite one, so let's look for that. Yeah, so this is probably my favorite one because you don't have to learn the concepts that can be hard sometimes. All you have to do is the exercises. So there's you don't even have to sign up. It should be unless it was changed, but last I was able to yeah, so look at this. Yeah, so gearing up. Last I heard of this course, when I took it, uh, uh, okay. So if you go to, oh shoot. Well, it looks like this kind of changed, but anyway, as I said, another great one is there's a data sign. So Data Quest. The Data Quest has some of the best this introduction to Python is free. They give you a free taste and then they ask you to pay. So it's just 3 hours. This is the absolute best course I think I've seen online, and it's free. So this is the one I recommend. Is if you want to learn Python. All right. So the next tool for AI ML is Jupyter Notebooks. I have mentioned earlier about Python being the preferred language, but how about the development environment? As network automation engineers, we have very much been used to editing raw scripts or sometimes using more advanced integrated development environments, IDEs, such as Microsoft Xcode. For the most part, the automation scripts are about executing some command, parsing the output of the command, and potentially taking some action back to the device. There has been little, if any, focus on the visual output of the Python script historically in the context of network and cloud automation. However, things are now changing. If you are reading this book, it is because you are more interested than ever in network telemetry, capturing data, and analyzing such data with some algorithm. You will likely need some type of visualization, such as data you collect pre-process or so pre-processing. You'll need a visualization for that, or a visualization for presenting the final results. Visualization is more vital than it was before. Your script is no longer just about running some logic out of a CLI command. It is about collecting data, analyzing, visualizing it, running business logic, presenting the results, etc., in an interactive manner. Traditional IDEs did not offer such capabilities, but now a different type of development environment offers a combination of code and output interactively, which we will refer to as notebooks. Probably the most well-known platform in this space is Jupyter Notebooks. It is an open source platform that enables you to create notebooks in a full Python, not limited to Python only, programming environment. It allows you to interleave code cells with the output of those cells, numeric output, graphs, etc., along with markdown formatted text that can be used to insert comments, documentation, or any other type of content, including images, HTML, etc. The result is a powerful programming environment while interactive and visually rich. The network and cloud automation community has yet to be widely exposed to the Jupyter Notebooks framework. In contrast, it has been the de facto development interface for the data science community for years. And I use Visual Studio Code. I started to kind of use this a bit, but honestly, it kind of makes the code odd. Like if you were to like package the code down or like move the code around, I feel like it kind of has you write the code differently than I'm used to, and it seems like it has you write the code for specific use cases, such as showing those visualizations that aren't widely applicable to other things, such as having an automated scheduled program that does things on your network. Like that doesn't necessarily require a visual interface. As the network and cloud automation community interest in data and analytics grows, and automation evolves to combine insights with actions rather than just automate actions. Because remember, we want to automate decisions. Jupyter Notebook will become a must-know tool for any network and cloud automation engineer. You may disagree, but I have the personal conviction that the Jupyter Notebook framework, or any of its variations or evolutions, such as Jupyter Labs, or cloud-hosted versions of it, such as Google's Colab, is the network automation interface of the future. In the practical use cases, I will be using Google's Colab. It is particularly convenient because, on the one hand, it is free. However, if you need to use GPUs or TPUs, you may upgrade to paid options such as Colab Pro or Colab Plus that will give you access to longer sessions, larger memory, and storage VMs, and faster compute engines leveraging GPU/TPUs. It also has the benefit that many of the required Python libraries are already pre-installed, so downloading and installing them is not needed. When using Python libraries in your own local environment, there are frequent challenges with dependencies and incompatibilities which require you to manage different virtual Python environments on your laptop. With Colab, all that is much simpler. I have built the use cases so that they can run in Colab, and you may run the notebooks on your laptop using a local Jupyter Notebook instance. You may need to change file paths, etc., but those are minor changes. So the key takeaway is that Jupyter Notebooks are, in my opinion, the network automation interface of the future. So that's quite a bit different. I've read another book on this channel, Automate Your Network by John Capobianco, and he was adamant about using VS Code. I think most automation environments, the developers use VS Code. So yeah, that's quite a change, quite a difference for something to advocate for. I can use both, but typically I have been using VS Code. But I can see where it might make more sense to use a combination of both. There are tools in Visual Studio Code to use a Jupyter Notebook. So yeah, that will take some getting used to for sure, because as I said, it requires writing the code in a little bit of a different way to optimize for those visualizations. All right, so this is exactly the time I wanted to end around, 8:45 or so. So that's it for this video. Now that I have the audio, sound check again. Thanks for watching, and see you in the next one.